Hello everyone, I am Pratigya and I welcome you to this tutorial on QUIC. QUIC stands for Quick UDP Internet Connections. In this session, we'll explore what QUIC is, why it was developed, what are its functionalities, advantages, disadvantages, and much more. Towards the end of the session, I'll also demonstrate quick traffic analysis using Wireshark. This tutorial is designed for anyone who already has a basic understanding of HTTP, TCP, and UDP. So let's get started. What is QUIC? So QUIC, which stands for Quick UDP Internet Connections, it is an Internet Transport Layer Protocol developed by Google in 2012. It was initially an experiment, but since had been adopted by major tech companies like Google, Meta, and Cloudflare. So QUIC is built on UDP, User Datagram Protocol, but it is combined with the best features of TCP and TLS. That means it offers both speed and security. Unlike TCP, which needs multiple handshakes to establish a secure connection, QUIC integrates transport and security handshakes into a single step, making the connections much more faster. Today, more than 8% of the websites use QUIC, and its adoption is growing very fast as it forms the foundation for HTTP 3. Um, so after like no, after having two very important transport layer protocols, UDP and TCP, we would think that did we actually need QUIC? So the traditional TCP could only provide reliable and ordered delivery, but it was slow. It required multiple round trips for connection and encryption setup. On the other hand, UDP was fast but not secure and didn't handle packet loss gracefully. So there comes QUIC. It resolves all these issues by reducing connection latency, improving the congestion control, and maintaining a TLS-grade encryption. Let's quick see how QUIC actually works. So the QUIC runs on UDP as we've already discussed, and each UDP datagram carries QUIC packets. These packets include a header and one or more frames. And the fields in a UDP datagram includes the source port, destination port, length, and checksum. So these are actually the same that we already know that exist in a UDP datagram. What is different is the concept of streams. So inside a QUIC packet, we have streams. So these are like independent lanes of traffic within one connection, and the streams can be unidirectional or bidirectional. And the stacking feature to see that these multiple streams can operate in parallel without blocking each other, something that TCP struggled with and which is commonly known as the head of line blocking. The QUIC handshake is much more faster than TCP plus TLS. QUIC uses multiple encryption levels, initial handshake, 0 RTT and 1 RTT. We will be discussing these while analyzing the network traffic on Wireshark. So through these 0 RTT resumption, clients can even send data immediately on reconnect in which actually reduces the latency further. The trade-off is that 0 RTT can be vulnerable to replay attacks, which we'll discuss in the security section. So here's a diagrammatic view. As we have already discussed, that a quick in a QUIC packet, the lanes that are the streams that run parallelly, which is not in the case of a TCP section. And even in this diagram, it can be seen that there's a HTTPS protocol over TCP and TLS takes multiple round trips and causes much more time to transfer data, while over QUIC, it happens quite instantly. Let's follow up by discussing the advantages of QUIC. Um, for till now, it's quite evident that we'll be talking about low latency and no head of line blocking. So head of line blocking is a performance bottleneck in a packet switch network where a single packet at the front of a queue prevents all of the subsequent packets from being processed, even if they're ready for different outputs or destination. So this occurs due to delays caused by issues in like network congestion or slow packet processing, which results in increased latency and reduced overall throughput. So this is the major factor that's been considered by a QUIC protocol. It it eliminates the head of line blocking, which makes the streams run more independently. It supports connection migration, it has its own built-in encryption, and not to mention provides an overall efficiency in the process of packet transfer. Now, everything has its own disadvantages. Talking about the disadvantages of QUIC protocol, um, I'll start with a complex implementation. Since QUIC is a very newer protocol and it's not been very much developed with all of the websites, so that's why it takes a while to actually implement its complex structure into the websites. Then there's an high CPU usage. Since everything is encrypted, it takes the more effort of a CPU in order to run as compared to TCP or UDP protocols. Also, there's a limited visibility for network operators. Since packet headers are hidden, it actually causes some problems for the network operators. Um, we also feel there are some complex debugging as compared to TCP. And sometimes fragmentation issues can also occur. So fragmentation is basically a process in which a large data packet is divided into a smaller segments, which are known as fragments. And sometimes, while actually transferring the data through QUIC, um, there could there could be some issues related to fragmentation. Now let's get into the bigger picture and see that how QUIC is deployed in real world application. We can see that majority of the browsers like Chrome, Edge, Firefox, and Safari supported through HTTP 3 protocol. Google services such as YouTube, Gmail, and Search also uses QUIC heavily. Meta uses QUIC across Facebook, Instagram, WhatsApp. All of these popular social media websites again run on QUIC. We do have some content delivery networks like Cloudflare and Akamai. They also offer QUIC-based delivery. Not to mention, even real-time services like gaming, video calls, and DNS are adopting QUIC for lower latency and reliability. All right, so this is how my Wireshark window looks like. I've captured some of the packets right here while exploring the Microsoft website on Google Chrome. After capturing like around like 9,000 something packages, I've stopped the I've stopped the transfer, and let's just quickly analyze the quick packets by displaying filter here. So the very first packet we see is the initial packet right here. So this basically this window explains all of the packets. Right here we can get the description, and here is the data in its hex values. So I was talking about the very first packet, which is the initial packet right here. So this replaces the TCP SYN and TLS's first handshake messages. It contains the basic connection setup information and carries the early TLS 1.3 handshake data inside QUIC. This allows the client and server to begin negotiating encryption keys immediately and reducing the connection times. Followed by this is the handshake packet. So if we want to, we can actually analyze this packet by opening all these navigation bars here, we can actually see the version of the QUIC packet, the destination and source connection IDs, what is the payload, and a packet number. So this packet number helps to stop the fingerprinting, and it provides much more encryption. Right here, ping, pairing, crypto, they all represent the frames of a QUIC packet. Talking about the handshake packet right here, these complete the TLS's 1.3 negotiation that started in the initial packet. Okay, all right. So at this stage, both sides agree on encryption keys and they establish a secure connection. Unlike TCP, where the handshake and TLS happen in separate layers, QUIC integrates them directly into its transport layer, making the setup more faster and more efficient. In some cases, we also notice a zero round trip packet. I can see if that's visible. Yeah. So for example, we just see a zero round trip packet right here. So this is a special feature of QUIC that allows the client to send early data when reconnecting to a server it has communicated with before. So the benefit that it causes is reduced latency, but again, as we discussed, the risk that this data can be replayed by attackers. That's why zero RTT is optional and be used carefully. Um, Talking about the one RTT, one round trip packet. In my capture, we mainly see the initial handshake packages. Um, and one round trip packets are not visible right here. So they are basically um, when the actual encrypted application data is exchanged. Since they are fully encrypted, Wireshark doesn't always label them explicitly or allows it to see the content. So what's more important is to see that the presence of short header packets indicates that the secure data exchange has begun. As we compare, the difference is very clear. So the TCP requires a three-way handshake consisting of SYN, ACK, and ACK followed by a separate TLS handshake. So that means more round trips before the data flows. With QUIC, we've seen how initial handshake, one RTT flow together in much more compact process. And even the encryption is much more stronger than TCP. All right, to sum up, the Wireshark window clearly shows how there's a very unique behavior shown by QUIC protocol, and this is the reason why it is much more incorporated in today's websites. Let's quickly talk about what are the security threats. Um, so the very first is that the attackers can exploit QUIC's handshake to amplify traffic towards a victim. We've already discussed this point that in a zero RTT handshake, that is much more vulnerable and that can break, that can cause attackers to get into the traffic. Again, like there are header and traffic analysis and denial of service attacks can also happen. So they can be mitigated by by applying rate limiting to verify clients' IPs before sending large responses. Even protections, replay protections, and unique tokens can be used for a handshake. Um, while analyzing the traffic, traffic padding and packet obfuscation should be used to hide size or timing of the packets, and even for the DDoS attacks, fake requests can be filtered by implementing connection rates, limiting, and early resource validation. I would wrap up by talking about the scalability of QUIC. QUIC is a modern transport layer protocol that combines the reliability of TCP and the speed of UDP. It powers major internet services today, offering lower latency, better security, scalability, while introducing new challenges in monitoring and compatibility. Thank you for watching this tutorial on QUIC.